Most people see fire ants as destructive pests that deserve nothing but elimination. But here's the shocking contradiction. In Argentina, these same feared insects are being farmed on an industrial scale as living biological weapons. Over 2 billion fire ants are produced annually in specialized facilities, creating a $180 million industry dedicated to sustainable pest control. While homeowners across North America spend millions trying to eliminate fire ant colonies from their yards, South American entrepreneurs are carefully breeding them in climate-controlled laboratories. These aren't just any fire ants. They're genetically selected super colonies designed to hunt down specific agricultural pests with surgical precision. The numbers are staggering. Argentina alone exports fire ant colonies to 28 countries, with each colony capable of protecting up to 50 hectares of crops. What was once considered an invasive nightmare has become one of the most sophisticated examples of biological warfare in modern agriculture. The industry grows by 15% annually, transforming rural communities into specialized breeding centers where entire families dedicate their lives to raising these tiny warriors. But this isn't just about pest control. It's about reimagining our relationship with nature itself. Join us as we dive into the hidden world of industrial fire ant farming, where science meets tradition, and where the line between innovation and ecological manipulation becomes increasingly blurred. The story of commercial fire ant farming begins in the 1980s, when Argentine researchers discovered that certain fire ant species could be conditioned to target specific agricultural pests while ignoring beneficial insects. What started as a desperate attempt to combat devastating crop losses has evolved into a billion-dollar industry that challenges everything we thought we knew about pest management. Fire ants possess unique characteristics that make them ideal biological control agents. Their aggressive territorial behavior, rapid reproduction rates, and adaptability to diverse environments create living pesticide systems that can operate continuously for months. Unlike chemical pesticides that degrade within days, a single fire ant colony maintains active pest control for an entire growing season. The economic importance cannot be overstated. Traditional chemical pest control costs farmers an average of $3,000 per hectare annually, with diminishing effectiveness as pests develop resistance. A fire ant colony costs just $850 and can eliminate up to 90% of target pests across 50 hectares, delivering cost savings of nearly 95% while maintaining superior results. Argentina produces over 2.3 million colonies annually, serving markets from Brazil to Southeast Asia. The primary buyers include organic farmers, government agricultural programs, and multinational corporations seeking sustainable alternatives to increasingly regulated chemical pesticides. Each colony contains between 50,000 to 200,000 individual ants, carefully balanced to maintain optimal hunting efficiency without becoming territorial threats to each other. The process transforms what nature created over millions of years into a precisely calibrated biological system, where every aspect from breeding to deployment is controlled by human expertise and cutting-edge technology. Everything begins with queen selection, a process as meticulous as breeding racehorses. Geneticists identify queens from wild colonies that demonstrate exceptional aggression toward target pests while showing minimal interest in beneficial insects like bees and butterflies. These queens undergo behavioral testing in controlled environments, facing various pest species to measure their hunting preferences and colony management skills. Selected queens are housed in climate-controlled facilities, maintained at exactly 20 acres, with 65% humidity, conditions that optimize egg production and larval development. Each queen receives a specially formulated diet consisting of high-protein cricket meal, honeydew extract, and vitamin supplements designed to maximize reproductive output. Under these conditions, a prime queen can produce up to 1,500 eggs daily, compared to 300-400 in wild conditions. The nursery chambers are architectural marvels of precision engineering. Temperature sensors monitor conditions to within 0.5 degrees, while automated feeding systems deliver measured portions of nutrients every 4 hours. The chambers feature removable glass panels that allow technicians to observe colony development without disturbing the delicate social structures that govern fire ant behavior. Worker ants begin emerging within 18 days of egg laying, immediately assuming specialized roles within the colony hierarchy. The first workers, called minims, focus exclusively on caring for developing larvae and maintaining nest hygiene. As the colony grows, larger workers called majors take over foraging duties and defensive responsibilities. The initial 30 days are critical for establishing colony identity and behavioral patterns. During this period, technicians introduce controlled amounts of target pest pheromones to condition the developing workers. This early exposure creates specialized hunting behaviors that persist throughout the colony's operational lifespan, ensuring that deployed ants will prioritize agricultural pests over non-target species. Quality control begins immediately, with daily monitoring of egg viability rates, larval development speed, and early worker behavior patterns. Colonies that fail to meet strict performance standards are eliminated before significant resources are invested in their development. Once colonies reach 5,000 individuals, the real conditioning begins. Workers are exposed to increasingly complex hunting scenarios, using live target pests in controlled laboratory environments. Successful pest elimination triggers reward feeding cycles, while exposure to beneficial insects results in neutral outcomes, gradually programming the colony to distinguish between valuable targets and protected species. The feeding regimen becomes highly specialized during this phase. Protein requirements increase dramatically as worker populations expand, demanding carefully balanced diets that maintain optimal aggression levels without triggering territorial conflicts between neighboring colonies. Feed composition includes ground termite protein, aphid extracts, and synthetic pheromone enhancers that sharpen hunting instincts. Advanced monitoring systems track colony behavior patterns 24 hours a day. Infrared cameras record movement patterns, feeding behaviors, and response times to introduced stimuli. Colonies that demonstrate exceptional performance metrics, fast target identification, high pest elimination rates, and stable social structure are marked for accelerated development and premium market placement. Temperature manipulation plays a crucial role in behavioral conditioning. Brief exposure to 35 degrees Celsius temperatures triggers heightened aggression responses, while periods at 25 degrees Celsius promote colony cohesion and cooperative hunting behaviors. This thermal conditioning creates colonies capable of rapid activation when deployed in field environments while maintaining operational stability during transport. The most challenging aspect involves preventing premature swarming behaviors that could compromise colony effectiveness. Specialized pheromone suppressors are introduced at precise intervals to maintain optimal population density without triggering reproductive cycles that would redirect energy away from pest control activities. By day 60, mature colonies contain 75,000 to 120,000 workers organized into efficient hunting units. Each colony undergoes final performance testing using standardized pest scenarios before receiving certification for commercial deployment. Success rates must exceed 85% pest elimination within 72 hours of introduction to target environments. Harvesting mature colonies requires precision timing and specialized equipment designed to minimize stress while preserving social structures. The optimal harvest window occurs when colonies reach peak hunter-worker ratios, but before reproductive swarming instincts begin developing. This typically falls between days 65 to 70 of the production cycle. The extraction process uses custom-designed vacuum systems that gently collect entire colonies while maintaining temperature and humidity conditions. Workers, larvae, and queens are carefully separated and placed in transport containers, engineered with breathable walls, climate control systems, and emergency food supplies sufficient for 10-day shipping periods. Different market segments demand different colony configurations. Premium organic farms receive colonies with 100,000 plus workers, optimized for broad-spectrum pest control across diverse crop types. Specialized applications, such as termite control in tree plantations, utilize smaller colonies of 50,000 workers specifically conditioned for subterranean hunting behaviors. Greenhouse operations require colonies modified with temperature sensitivity that prevents overwintering survival, ensuring controlled deployment periods. Market values vary significantly based on colony specifications and conditioning levels. Standard agricultural colonies sell for $850 each, while specialized colonies for organic certification or specific pest species command prices up to $1,400. Premium breeding stock for establishing new production facilities can reach $3,500 per queen, reflecting the extensive genetic selection and behavioral conditioning invested in their development. Distribution networks span across South America, with colonies shipped via temperature-controlled transport to Brazil, Paraguay, and Uruguay within 48 hours of harvest. International exports require specialized containment systems and documentation, proving the colony's inability to establish permanent populations outside target agricultural areas. Each shipment includes detailed deployment instructions, performance monitoring protocols, and emergency containment procedures. Quality assurance continues through harvest and shipping, with each colony receiving unique identification codes that allow tracking from production facility to field deployment, ensuring complete traceability throughout the supply chain. The fire ant farming industry employs over 12,000 people across Argentina, creating economic opportunities in rural regions previously dependent on traditional livestock farming. Specialized roles range from queen geneticists earning $65,000 annually to colony technicians starting at $32,000, with experienced workers commanding salaries comparable to urban manufacturing jobs. Family operations have emerged throughout the provinces of Buenos Aires, Santa Fe, and Córdoba, where multi-generational knowledge of ant behavior combines with modern biotechnology to create highly efficient production systems. These family farms typically manage 200 to 300 breeding colonies simultaneously, generating annual revenues between $400,000 and $650,000, while providing employment for 8 to 12 family members and seasonal workers. Export revenues contribute significantly to Argentina's agricultural trade balance. Colony exports generated $167 million in 2023, with growth projections indicating potential revenues of $280 million by 2027. Major destination markets include Brazil, 43% of exports, Paraguay, 18%, Bolivia, 12%, and emerging markets in Southeast Asia, accounting for the remaining 27%. The industry's impact extends beyond direct employment to supporting sectors including specialized transport, containment equipment manufacturing, and research institutions dedicated to biological pest control development. Universities in Buenos Aires and Rosario have established dedicated entomology programs specifically focused on commercial ant farming, graduating 150-200 specialists annually. Comparative economic analysis shows fire ant farming delivers higher per hectare returns than traditional cattle ranching while requiring 70% less land usage. A 100-hectare facility can produce colonies capable of protecting 5,000 hectares of crops, creating economic multiplier effects that benefit entire regional economies. Rural communities have transformed from struggling agricultural support centers into specialized biotechnology hubs, with former cattle ranchers retraining as colony managers and veterinarians, specializing in insect health management, demonstrating remarkable adaptability in traditional farming regions. The deliberate breeding and deployment of aggressive insect species raises profound questions about humanity's role in manipulating natural ecosystems. While proponents celebrate reduced chemical pesticide usage and improved crop yields, critics warn of potential ecological disasters if these conditioned fire ant colonies adapt beyond their intended parameters or establish unauthorized breeding populations. Environmental scientists present conflicting perspectives on long-term sustainability. Supporters argue that biological pest control represents evolution in agricultural practice, reducing toxic chemical loads that harm soil microorganisms, pollinating insects, and water systems. Opposition voices express concern about introducing non-native species into delicate ecological balances, pointing to historical disasters like kudzu and zebra mussels as warnings against biological manipulation. Worker welfare within the industry presents additional ethical dimensions. While employment opportunities benefit rural communities, critics question whether workers receive adequate protection from ant stings and exposure to conditioning chemicals used in colony development. Industry standards require protective equipment and regular health monitoring, but independent oversight remains limited. Animal welfare considerations focus on the treatment of millions of insects bred for commercial purposes. Though fire ants lack complex nervous systems comparable to mammals, ethical frameworks struggle to address the moral implications of mass insect farming designed to create more efficient killers. The sustainability paradox becomes apparent when considering that successful biological pest control could reduce biodiversity by eliminating target species that serve as food sources for other wildlife. What happens to ecosystems when highly efficient predators remove substantial portions of the food chain? As this industry continues expanding globally, we must ask ourselves, are we witnessing revolutionary agricultural innovation or playing dangerous games with forces beyond our complete understanding? The answer may determine whether biological pest control represents humanity's partnership with nature or another step toward ecological manipulation with unpredictable consequences. What's your perspective on using one species to control another? Brilliant innovation or risky interference? Share your thoughts in the comments below. And don't forget to subscribe for more investigations into the hidden industries shaping our world.